Java Multithreading Debugging using Java Introduction. Java Multithreading Debugging is the process of finding and fixing issues in Java applications that use multiple threads running at the same time. Backend developers often learn Java multithreading debugging to fix deadlocks, race conditions, thread starvation, high CPU usage, memory visibility issues, blocked threads, slow APIs, concurrency bugs, production performance issues, thread pool problems. A common learning topic is: how can Java backend developers debug multi-threading issues effectively? This guide explains Java thread basics, multi-threading problems, deadlock debugging, race condition debugging, thread dumps, thread states, synchronized debugging, ExecutorService debugging, CompletableFuture debugging, Spring Boot thread issues, production debugging tools, best practices, interview questions. This is one of the best practical guides for Java backend developers learning multithreading debugging. Simple definition. Java multithreading debugging means identifying why multiple threads are not working correctly in a Java application. Simple example. Thread A updates value. Thread B reads value. Thread C modifies same value. If not handled correctly, the application may produce wrong output, slow response, blocked request, infinite waiting, high CPU usage, random production bugs. Why backend developers need multithreading debugging? Backend developers work with REST APIs, background jobs, schedulers, Kafka consumers, database calls, file processing, async APIs, batch jobs, thread pools, microservices. Java applications often run many threads at the same time. Example: Tomcat request threads, Kafka consumer threads, scheduler threads, async executor threads, database connection threads, garbage collector threads. So, backend developers must know how to debug thread-related problems. Java thread basics. A thread is a small unit of execution inside a Java process. Example: thread equals new thread, even at print line, running in another thread. Thread start. Output, running in another thread. Important: thread.start creates a new thread. Thread.run does not create a new thread. Java thread states. State meaning new, thread created but not started. Runnable, running or ready to run. Blocked, waiting to enter synchronized block. Waiting indefinitely. Timed waiting for specific time. Understanding thread states is very important for debugging. Common multithreading problems. Problem meaning race condition. Multiple threads update shared data incorrectly. Deadlock, threads wait for each other forever. Starvation, a thread never gets CPU resource. Livelock, threads keep reacting but make no progress. Visibility issue, one thread cannot see another thread's update. Leak threads keep increasing and never stop. Pool exhaustion, thread pool has no available threads. High CPU, threads are running too much or looping. Step 1. Understand race condition. Race condition happens when multiple threads access shared data and final result depends on timing. Example: public class counter. Private int count equals 0. Public void increment. Count plus plus. Public int get count. Return count. Problem: count plus plus is not atomic. It actually means read count, increase count, write count. Multiple threads can interfere. Step 2. Debug race condition. Example test. Public class race condition demo. Public static void main string args throws interrupted exception. Counter equals new counter. Thread T1 equals new thread, where for int I equals 0, I less than 10,000, I plus plus. Counter increment. Thread T2 equals new thread x for int I equals 0, I more than 10,000, counter increment. T1 dot start. T2 dot start. T1 join. T2 join. System.out.println counter.getCount. Expected, 2,000. Possible actual output, 18,452, 19,320, 1991. This random output indicates a race condition. Step 3. Fix race condition with synchronized public class counter. Private int count equals 0. Public synchronized void increment. Public int get count. Return count. Now only one thread can execute increment at a time. Simple idea. Synchronized protects shared mutable state. Step 4. Fix race condition with AtomicInteger. Better for simple counters. Import java.util.concurrent.atomic.AtomicInteger. Public class counter. Private final AtomicInteger count equals new AtomicInteger 0. Public void increment. Count increment and get. Public int get count. Return count.get. Benefits. Thread safe. Simple. Efficient. Good for counters. Step 5. Understand deadlock. Deadlock happens when 2 or more threads wait for each other forever. Example. Thread A holds lock 1 and waits for lock 2. Thread B holds lock 2 and waits for lock 1. Result? Both threads are stuck forever. Step 6. Deadlock example. Public class deadlock demo. Private static final object lock 1 equals new object. Private static final object lock 2 equals new object. Public static void main string args. Thread T1 equals new thread. Enter synchronized lock 1. System out.println thread 1 locked lock 1. Synchronized lock 2. System.out.println thread 1 locked lock 2. Thread T2 equals new thread. Synchronized lock 2. System.out.println thread 2 locked lock 2. Synchronized lock 1. System.out.println thread 2 locked lock 1. T1.start. T2.start. Problem? Thread 1 locks lock 1, then waits for lock 2. Thread 2 locks lock 2, then waits for lock 1. Step 7. Debug deadlock using thread dump. A thread dump shows C thread names, C thread states, C stack traces, C locks held, C locks waiting, deadlock details. Command JPS. Find Java process ID. Then jstack PID. Example, jstack 12345. You may see found one Java level deadlock. This is a strong signal. Step 8. Read thread dump. Thread dump example. Thread 1 blocked waiting to lock 0x001. Locked 0x002. Thread 2 blocked waiting to lock 0x002. Locked 0x001. Meaning, thread 1 waits for lock owned by thread 2. Thread 2 waits for lock owned by thread 1. That is a deadlock. Step 9. Fix deadlock with lock ordering. Always acquire locks in the same order. Bad. Thread 1. Lock 1 means lock 2. Thread 2. Lock 2 means lock 1. Better. Thread 1. Lock 1 means lock 2. Thread 2. Lock 1 means lock 2. Fixed example. Synchronized lock 1. Synchronized lock 2. Key idea. Consistent lock ordering prevents many deadlocks. Step 10. Debug blocked threads. Blocked means blocked. Thread is waiting to enter a synchronized block or method. Example. Tomcat exec12 blocked waiting to lock user service. Possible causes. Synchronized method is slow. Too much code inside lock. Database call inside synchronized block. Network call inside lock. Bad example. Public synchronized. User get user. Long ID. Return user repository find by id. Or else throw. Problem. Database call happens while holding lock. Better. Public user get user. Long ID. Return user repository find by ID, or else throw. Use synchronization only when needed. Step 11. Understand waiting threads. Waiting means thread is waiting indefinitely for another thread or signal. Common causes: object.wait, safe, thread.join, locksupport.park, CompletableFuture.get, countdownLatch.await. Example: latch.await. If countdown never happens, thread waits forever. Step 12. Debug waiting threads. Check. What is the thread waiting for? Who should wake it up? Is countdown called? Is notify called? Is future completed? Example issue: countdown latch equals new countdown latch 1. Latch await, but missing latch countdown. Fix. Try work. Finally, latch countdown. Step 13. Understand timed waiting threads. Timed waiting means thread is waiting for a specific time. Common causes: thread.sleep, wait timeout, join timeout, scheduled tasks, blocking queue polling, HTTP client timeout, database connection timeout. Example: thread.sleep 5000. In thread dump. Timed waiting. This is not always a problem. It becomes a problem when many important threads are sleeping or waiting too long. Step 14. Debug high CPU threads. High CPU usually means infinite loop, busy waiting, too many threads, heavy computation, excessive logging, serialization issue, regex issue, garbage collection pressure. Debug steps. 1. Find Java process ID. 2. Find high CPU thread ID. 3. Convert thread ID to hex. 4. Match it in thread dump. 5. Read stack trace. Linux command. Top H P PID. Convert thread ID to hex. Printf %x n. Then search for mid equals 0x x s in thread dump. Step 15. High CPU example. Bad code. While true. No sleep, no blocking, no exit condition. Problem: thread consumes CPU continuously. Better. While running, process thread.sleep 100. Or use blocking queue scheduled ExecutorService Kafka listener instead of manual busy loop. Step 16. Understand visibility issues. Visibility issue happens when one thread updates a variable, but another thread does not see the latest value. Bad example: public class stop flag demo. Private boolean running equals true. Public void stop running equals false. Public void run. While running, keep running. Problem: another thread may not see running equals false. Step 17. Fix visibility with volatile public class stop flag demo. Private volatile boolean running equals true. Public void stop running equals false. Public void run. While running, keep running. Volatile ensures visibility. Use volatile for check flags, simple state visibility, stop signals. Do not use volatile for compound operations like count plus plus. For counters, use AtomicInteger. Step 18. Debug ExecutorService issues. ExecutorService is commonly used in backend applications. Example: ExecutorService executor equals executors.new fixed thread pool executor.submit lamp process task : Common problems: pool too small, pool too large, queue grows forever, tasks never finish, exceptions swallowed, shutdown not called, deadlock inside executor. Step 19. ExecutorService debugging checklist. Check. Pool size, active thread count, queue size, completed task count, rejected task count, task execution time, exception handling, shutdown behavior. Better use thread pool executor directly for monitoring. Thread pool executor equals new thread pool executor 10, 20, 60 time unit dot seconds new array blocking queue. You can inspect executor.getActiveCount, executor.getQueue.size, executor.getCompleted task count. Step 20. Avoid unbounded queues. Bad. Executors.new fixed thread pool 10. This uses an unbounded queue internally. Problem. If tasks arrive faster than processing, memory can grow. Better. Thread pool executor is new thread pool executor 10, 20, 60 time unit dot seconds new array blocking queue of 500 new thread pool executor caller runs policy. Benefits. Check bounded queue, back pressure, better production control. Step 21. Debug CompletableFuture. Example. CompletableFuture string future equals CompletableFuture.supply async D2P. String result equals future get. Common issues. Caps. Blocking with get. Using common fork join pool accidentally. Exceptions not handled. Chained tasks not running. Deadlock due to same executor. Timeout missing. Better. Future.or timeout 3 time unit seconds dot exceptionally ex equals fallback. Step 22. CompletableFuture best practice. Use custom executor. ExecutorService executor equals executors new fixed thread pool 10. CompletableFuture string future equals CompletableFuture.supply async call API executor or timeout 3 time unit seconds exceptionally x dot fallback. Why? Avoids overloading common pool. Check. Easier monitoring. Predictable behavior. Better production debugging. Step 23. Debug Spring Boot thread issues. Spring Boot applications commonly use Tomcat request threads, @async threads, scheduler threads, Kafka listener threads, database connection pool threads, HTTP client threads. Example thread names. HTTP NIO 8080 exec1, task 1, scheduling 1, Kafka consumer 1, Hikari pool 1. Thread names help identify the source. Step 24. Debug Tomcat thread pool. Tomcat handles HTTP requests using worker threads. Symptoms. APIs hang. All requests slow. Many threads blocked. Many threads waiting on DB. High response time. Possible causes. Check database pool exhausted. Check slow external API. Check synchronized bottleneck. Check thread pool too small. Check no timeout. Check blocking calls. Check but HTTP NIO 8080 exec threads. In thread dump. Step 25. Debug database connection pool blocking. Common production issue. Tomcat threads waiting for database connection. Example stack trace. com.zaxer.hikari.pool.hikaripool.getConnection. Meaning, threads are waiting for DB connections. Possible causes. Connection leak, slow queries, pool size too small, transactions open too long, database overloaded. Fixes. Close connections properly. Tune HikariCP pool size. Optimize queries. Add indexes. Reduce transaction scope. Monitor active connections. Step 26. Debug @async issues. Example. @async. Public void send email. Email service.send. Common problems. @enable async missing. Method called from same class. Executor not configured. Exceptions lost. Pool too small. No timeout. Correct setup. Enable async. @configuration. Public class. Async config. Custom executor. BP public executor. Task executor. Thread pool task executor equals new thread pool task executor. Executor.set core pool size 5. Executor.set max pool size 10. Executor.set queue capacity 100. Executor.set thread name prefix app async. Executor.initialize. Return executor. Step 27. Debug scheduled jobs. Example. At scheduled. Fixed delay equals 5,000. Public void process job. Common issues. Check. Job runs too long. Overlapping execution. Single scheduler thread blocked. Exception stop logic. Database lock conflict. No timeout. Best practices. Quote. Log start end time. Avoid long transactions. Handle exceptions. Use distributed lock if multiple instances. Monitor execution time. Step 28. Thread dump tools. Useful tools. Tool purpose. jstack. Generate thread dump. JCMD. JVM diagnostics. Visual VM. Visual thread monitoring. JConsole. JVM monitoring. Java mission control. Advanced profiling. IntelliJ debugger. Local debugging. Spring Boot actuator. Production insights. Prometheus Grafana. Metrics monitoring. Useful commands. jcamd PID. Thread.print jstack PID. Step 29. Debugging with IntelliJ IDEA. Useful IntelliJ features. Cog. Thread view. Breakpoint per thread. Suspend all threads. Suspend one thread. Evaluate expression. Stack trace inspection. Variable watches. Conditional breakpoints. Tips. Use thread names. Use conditional breakpoints. Avoid stopping all production-like flows unnecessarily. Example conditional breakpoint. User ID equals 101. Step 30. Production debugging strategy. For production, avoid random guessing. Follow this process. 1. Check symptoms. 2. Capture thread dump. 3. Capture CPU memory metrics. 4. Check logs with correlation ID. 5. Identify stuck threads. 6. Identify blocking resource. 7. Check DB external API latency. 8. Apply safe fix. 9. Add monitoring. 10. Prevent recurrence. Important. 1 thread dump may not be enough. Take 3 thread dumps 10 to 15 seconds apart. If the same stack appears repeatedly, that is likely the problem area. Real-world case study 1. API hanging symptom / API orders is hanging. Users wait for 60 seconds. Thread dump shows HTTP NIO 8080 exec 10 waiting at com.zaxer.hikaripool.hikaripool. Meaning, request threads are waiting for database connections. Root causes. Check DB connection leak. Check slow queries. Check long transaction. Check pool too small. Fix. Check connection leak logs. Optimize query. Add index. Reduce transaction time. Tune Hikari pool. Real-world case study 2. Deadlock in payment service symptom payment API freezes randomly. Thread dump shows. Found 1 Java-level deadlock. Cause. 2 synchronized blocks. Acquire locks in different order. Fix. Cross. Use consistent lock order. Cross. Reduce synchronized scope. Cross. Replace synchronized with reentrant lock timeout. Real-world case study 3. High CPU in worker symptom. CPU is 95%. Application response is slow. Investigation. Top. HP. PID. JStack. PID. Match. NID. Thread stack shows. While loop. Inside. Retry worker. Cause. Busy waiting without sleep or blocking queue. Fix. Add proper wait. Check. Use blocking queue. Use scheduled executor service. Add backup strategy. Java multithreading debugging checklist. When debugging, check. Key thread dump. Check thread state. Stack trace. Lock owner. Blocked threads. Waiting threads. CPU heavy threads. Executor queue size. DB connection pool. External API timeout. Synchronized blocks. Infinite loops. Missing timeout. Thread leak. Memory pressure. Common beginner mistakes. 1. Using synchronized everywhere. Too much synchronization causes blocking and poor performance. Better. Synchronize only shared mutable state. 2. Ignoring thread dumps. Thread dumps are one of the best tools for Java thread debugging. 3. Using unbounded thread queues. Unbounded queues can cause memory issues. Use bounded queues. 4. Blocking inside CompletableFuture. Bad. Future.get inside another async task can cause thread starvation. Better. Then apply, then compose, or timeout, exceptionally. 5. Missing timeouts. Always add timeouts for external API calls, database calls, future operations, queue polling, locks if possible. 6. Not naming threads. Bad. Pull 1 thread 1. Better. Payment worker 1, email async 1, order processing 1. Thread names make debugging easier. 7. Ignoring exceptions in async code. Async exceptions may not appear clearly. Always handle. Exceptionally handle when complete best practices. Understand thread states. Use thread dumps. Name custom threads. Keep synchronized blocks small. Avoid nested locks. Use concurrent collections. Use AtomicInteger for counters. Use volatile for simple flags. Use ExecutorService instead of manual threads. Configure bounded queues. Monitor thread pools. Add timeouts. Avoid blocking common fork join pool. Use custom executor for async tasks. Handle async exceptions. Take multiple thread dumps. Monitor DB connection pool. Avoid long transactions. Log correlation IDs. Test concurrency with repeated runs. Useful Java concurrency classes. Class, purpose. Thread, basic thread. Runnable, task without return. Callable, task with return. ExecutorService, thread pool. CompletableFuture, async programming. AtomicInteger, thread safe counter. Concurrent hash map, thread safe map. Countdown latch, wait for events. Semaphore, limit concurrent access. Re-entrant lock, advanced locking. Blocking queue, producer consumer pattern. Debugging commands. Find Java process. JPS. Thread dump. jstack. PID. Alternative. JCMD. PID. Thread.print. High CPU thread check. Top-H-P. Convert thread ID to hex. Printf %x n thread ID. Heap and JVM info. JCMD, PID, VM info, interview questions. 1. What is a thread in Java? A thread is a lightweight unit of execution inside a Java process. 2. What is a race condition? A race condition happens when multiple threads access shared data, and the final result depends on timing. 3. How do you fix a race condition? Use check, synchronized, locks, atomic classes, concurrent collections, immutable objects. 4. What is a deadlock? Deadlock happens when 2 or more threads wait for each other forever. 5. How do you debug deadlock? Use thread dumps with jstack, PID. Then check blocked threads and locks. 6. What is the difference between blocked and waiting? State meaning. Blocked, waiting for monitor lock. Waiting, waiting for signal or another thread. 7. What is volatile? Volatile ensures visibility of variable updates between threads. 8. Is volatile enough for count++? No. Count++ is not atomic. Use AtomicInteger 9. Why use ExecutorService? ExecutorService manages thread pools and avoids creating threads manually for every task. 10. Why avoid unbounded queues? Unbounded queues can grow indefinitely and cause memory problems. 11. How do you debug high CPU in Java? Use top-H-P PID, jstack PID, match NID with thread dump 12. What causes thread starvation? Thread starvation happens when a thread cannot get CPU or required resources because other threads keep using them. Java Multithreading Debugging Roadmap, beginner level. Learn: thread, runnable, synchronized, volatile, AtomicInteger, thread states, race condition, deadlock basics. Build: counter race condition demo, intermediate level. Learn: check ExecutorService, check thread pool executor, check CompletableFuture, check blocking queue, check countdown latch, check thread dumps, high CPU debugging, build, producer consumer system, advanced level, learn, catching, Spring Boot thread pools, Tomcat threads, HikariCP blocking, Kafka consumer threads, async debugging, production thread dump analysis, monitoring. Spring Boot Async Order Processing System 30-Day Learning Plan, Week 1, Java Thread Basics. Learn. A key thread, a key runnable, a key start versus run, a key join, a key sleep, a key thread states, a key synchronized. Practice. Create multiple threads and print output. Week 2, Race conditions and deadlocks. Learn. Shared state, race condition, AtomicInteger, volatile, deadlock, lock ordering. Practice. Build counter race condition demo. Build deadlock demo. Fix both issues. Week 3, executors and async. Learn. ExecutorService, executor thread pool executor, bounded queues, CompletableFuture, timeout handling, async exception handling. Practice. Build async task processor. Monitor active threads and queue size. Week 4, production debugging. Learn. Check jstack, JCMD, Visual VM, IntelliJ thread debugging, Spring Boot thread pools, Tomcat threads, HikariCP blocking. Practice. Analyze thread dumps, debug deadlock, debug high CPU, debug blocked DB threads. Real-world Spring Boot example, order processing system. Architecture, REST API, order service, async executor, payment API, inventory API, database. Possible issues. Call, payment API timeout missing, async pool exhausted, database connection pool blocked, order lock deadlock, CompletableFuture exception ignored. Debugging approach. Check logs, check thread dump, check executor metrics, check DB pool metrics, check external API latency. Final summary. Java multithreading debugging is an essential skill for backend developers. Important concepts include
thread states, race conditions, deadlocks, synchronization, volatile, atomic classes, ExecutorService, CompletableFuture, thread dumps, high CPU debugging, Spring Boot thread pools, database connection blocking. Backend developers already work with REST APIs, Kafka consumers, Kafka schedulers, async jobs, databases, microservices. So, multithreading debugging is very useful in real-world backend systems. Key idea. Java multithreading debugging is about understanding what each thread is doing, what resource it is waiting for, and why progress is blocked or incorrect.